students, so welcome back to my video lecture 5 on hydrogen and its compounds. So in the previous video I think we started with a new compound of hydrogen. What was it? Hydride. Okay, hydride. So far we have finished up to dihydrogen. Okay, we have finished dihydrogen. So in the last class we studied the introduction to hydrides. Okay, I have told you what are hydrides and how hydrides are classified. How hydrides are classified? Hydrides are classified into three types. Which are those three types? Yes, ionic or saline hydride, ionic or saline hydride. Next, covalent, okay, or molecular hydrides, okay, molecular hydrides. And lastly, okay, yes, metallic or non-stoichiometric hydrides, understood? So in this video we will be talking about these three different hydrides in detail. So first I'm going to start with ionic or saline hydride. Okay, yes. So first let us start with ionic or saline hydride. Okay, ionic or saline hydride. Yes. Okay, well, look here, first one, I'm talking about the first one. Let us learn in terms of points. Okay, that will be easy for you to remember. Okay, so I'll be talking about what? Ionic or saline hydrides. Okay, saline hydrides, understood? Okay, well, when do you get ionic or saline hydrides? See, if hydrogen combines with S block elements, if hydrogen combines with what? S block elements, the resultant hydrides are called as ionic or saline hydrides. Okay, if hydrogen combines with S block elements, the resultant hydrides are called as ionic or saline hydrides. For example, okay, so we know in S block we have alkali metals and alkaline earth metals, isn't it? If alkali metals like sodium, potassium, okay, lithium, etc., if alkali metals combines with hydrogen, they form metal hydrides of the type MH, isn't it? Okay, where M might be what? Sodium, potassium, rubidium, okay, cesium, isn't it? And if alkaline earth metals combines with hydrogen, they form metal hydrides with the formula MH2. So this MH and MH2, for example, sodium hydride, calcium hydride, okay, sodium hydride and calcium hydride are what type of hydrides? They are ionic or saline hydrides. Are you getting it? Ionic or saline hydrides, understood? Okay, so like this, if hydrogen combines with S block elements, they form hydrides, and those hydrides are called as ionic or saline hydrides. What are the characteristics of these ionic or saline hydrides? See, remember, okay, these ionic or saline hydrides are always stoichiometric in nature. They are all stoichiometric in nature. What do you mean by stoichiometric nature? They'll have a fixed, okay, whole number ratio, okay. Stoichiometric in nature means they will have a fixed whole number ratio. If I take sodium hydride, what is the ratio here? 1:1, isn't it? If I take calcium hydride, okay, yeah, here what is the ratio? It is 1:2. They are stoichiometric in nature. That means they know what? They prefer fixed whole number ratio. Okay, got it? And what are the other properties of ionic or saline hydrides? Okay, see, whenever these ionic hydrides or saline hydrides are electrolyzed, whenever they are electrolyzed, they always liberate hydrogen gas. They always liberate what? Hydrogen gas. Are you getting my point? For example, when calcium hydride is electrolyzed, whenever they are electrolyzed, what? Okay, they liberate hydrogen gas. Liberate what? Hydrogen gas. They are stoichiometric in nature. Okay, and whenever they are electrolyzed, they produce what? They produced, okay, yeah, they liberate hydrogen gas, isn't it? Okay, and in all these ionic or saline hydrides, okay, the oxidation state of hydrogen is going to be -1. Okay, in all these hydrides, the oxidation state of hydrogen is going to be -1. In ionic hydrides or saline hydrides, what is the oxidation state of hydrogen? It is going to be -1. They're all colorless. And they are crystalline in nature. I hope you understood. Yes, students. So this is all about ionic hydrides. Okay, yes, when hydrogen combines with S block elements, they form hydrides, and those hydrides are called as ionic or saline hydrides. They are stoichiometric in nature, they are colorless, they are crystalline, and whenever they are electrolyzed, they liberate what? Hydrogen gas. That's correct. Now let us talk about covalent hydrides. That is what is most important. Covalent hydrides. Okay, yes, covalent hydrides. Yeah, okay, if I talk about covalent hydrides, see this, covalent hydrides, okay, see, whenever hydrogen combines with p block elements, when hydrogen combines with what? P block elements, okay, it forms hydrides, and these hydrides are called as covalent hydrides, or else they are also called as molecular hydrides. Okay, when hydrogen combines with p block elements, they form hydrides, and these hydrides are called as covalent or molecular hydrides. Well, covalent or molecular hydrides are again classified into three types. They are again classified into three types. Okay, what are those three types? They are electron deficient, okay, electron precise, and electron rich. Covalent hydrides are again classified into three types: electron deficient, electron precise, and electron rich. Okay, what is electron deficient? Let us take up the examples, certain examples like BH3, ALH3. All these are what? Electron deficient hydrides. Why they are called as electron deficient hydrides? If you look at boron, okay, if you write the Lewis dot structure of boron will have 3 electrons in its outermost shell. Okay, so boron will have 3 electrons in its outermost shell. Now these 3 electrons in the outermost shell of boron will be, okay, shared with the 3 electrons of hydrogen. Okay, so these 3, okay, outermost electrons of boron will be shared with the 3 electrons of hydrogen, isn't it? Yes, hydrogen, and it forms what? BH3, boron. Okay, isn't it? Now what is it called as? Any idea? What is this molecule called as? Borane. Okay, yes, observe here, observe the, okay, yes, outermost electronic configuration of boron here. See, boron in its outermost orbital, in its outermost shell, has only 6 electrons. Okay, even though boron has combined with hydrogen, in its outermost shell it has only 6 electrons. 2, 4, 6. Okay, it is still deficient of 2 more electrons to complete its octet, isn't it? It is still deficient of 2 more electrons to complete its octet. Hence, boron is electron deficient. It is ready to accept 2 more electrons to complete its octet. These type of hydrides are called as electron deficient hydrides. These are called as what? Electron deficient hydrides. Now, if any species which can give, okay, electrons to boron. So boron is will easily accept the electrons. Boron will easily accept the electrons because it requires 2 more electrons to complete its octet. Okay, understood? Boron requires 2 more electrons to complete its octet. So boron will easily take the electrons if any other species is ready to give the electrons. So we have learned this type in equilibrium, chemical equilibrium. Electron deficient species are called as what? Lewis acids, isn't it? Okay, they are electron deficient and they are ready to accept the electrons. They are electron deficient and they are ready to accept the electrons. Such type of hydrides are called as electron deficient hydrides. Now, when do you get electron deficient hydrides? See, if hydrogen combines with 13th group elements, if hydrogen combines with 13th group elements, as I said, boron, aluminium, etc., etc. Okay, if hydrogen combines with 13th group elements, it will form electron deficient species. They will be deficient of electrons in their outermost shell. They are ready to accept the electron. They are electron acceptors. That is why they are also regarded as what? Lewis acids. They are also regarded as Lewis acids. Understood? So that's about electron deficient hydrides. Now, if you go with electron precise hydrides. When do you get electron precise hydrides? Okay, if hydrogen reacts with 14th group elements. If hydrogen reacts with 14th group elements like carbon, silicon, etc., etc., okay, it will form electron precise hydrides. Okay, what do you mean by electron precise? Look here, we know if you write the Lewis dot structure of carbon, okay, we know carbon has 4 electrons in its outermost shell, isn't it? 4 electrons in its outermost orbit. Now this carbon, okay, will share 4 electrons with 4 hydrogen atoms, okay, with 4 hydrogen atoms, and it forms methane. Look at here, methane. Okay, now observe, okay, yes, 2 electrons, 2 electrons, 2 electrons, 2 electrons. How many electrons are there around carbon in its outermost shell now when it combines with hydrogen? When carbon combines with hydrogen, okay, it will have 8 electrons in its outermost shell. It is sufficient. It is, okay, it is now surrounded by sufficient number of electrons, isn't it? It is precise. It is, okay, neither deficient nor rich of electrons. It wants to have 8 electrons in its outermost shell. Now when it combines with hydrogen, it has 8 electrons in its outermost shell. It is electron precise. It is electron precise. So around carbon there are sufficient number of electrons to complete octet. Hence such type of compounds are called as what? Electron precise, okay, hydrides. Okay, for example, one more example, even silane, SiH4, this is also an example for electron precise hydride. Okay, if you look at silicon, okay, silicon just like carbon, it will have 4 electrons in its outermost shell. It will share 4 electrons with 4 hydrogen atoms, okay, and it forms silane, SiH4. Now just check the number of electrons around silicon, 8 electrons. Okay, it wants to have 8 electrons and it has 8 electrons, therefore it is electron precise. Electron precise. So like this, whenever hydrogen combines with 14th group elements like carbon and silicon, it will form electron precise hydrides. Okay, is that simple? Now what about electron rich hydrides? What about electron rich hydrides? Look here, if hydrogen combines with 15th group, 16th group and 17th group elements. Okay, if hydrogen combines with 15th group, 16th group and 17th group elements like nitrogen, oxygen, fluorine. Okay, like what? Nitrogen, oxygen and fluorine. It will form what type of hydrides? It will form electron rich hydrides, isn't it? Okay, if hydrogen combines with 15th group, 16th group, 17th group, okay, elements like nitrogen, oxygen, fluorine, it will form electron rich hydrides. For example, ammonia is an electron rich hydride. Okay, why it is electron rich? Because nitrogen will have a lone pair of electrons. Water, H2O, is an electron rich hydride. Why water is an electron rich hydride? Because oxygen will have two lone pair of electrons. Okay, hydrogen fluoride is an electron rich hydride. Why hydrogen fluoride is an electron rich hydride? Because it will have three lone pair of electrons. Three lone pair of electrons. Are you getting my point? If you look at the structure of ammonia, observe here, nitrogen has 5 electrons in its outermost shell. It has 5 electrons in its outermost shell. Nitrogen will share only 3 electrons to form bond with hydrogen, and 2 electrons are not involved in bond formation. Even though the octet structure of nitrogen is complete, even though 2, 4, 6, 8, even though the octet structure of nitrogen is complete, these electrons are not involved in bond formation. They are available for donation. Hence, nitrogen becomes electron rich. It is ready to donate these 2 electrons. It is ready to donate these 2 electrons. It is electron rich. If you look at the structure of water here, yes, oxygen, okay, yes, oxygen will have how many electrons in its valence? Okay, yes, around it, yes, any idea? Oxygen will have 6 electrons in its outermost shell. Okay, oxygen will have 6 electrons in its outermost shell. It will share only 2 electrons with hydrogen to form bond. Okay, and the 2 pair of electrons are not involved in bond formation. They are available for donation. Therefore, that means oxygen becomes electron rich. It is rich of 4 electrons, or it is rich of 2 pair of electrons which can be donated. Hence, water is an electron rich species. Like this, if hydrogen combines with 15, 16 and 17 group elements, it will form what type of hydrides? Electron rich hydrides. They are rich of electrons, and these electrons can be donated. That means these hydrides will act as electron donors. If they act as electron donors, yes, we have learned, if they act as electron donors, they behave as what? Lewis base, isn't it? They behave as Lewis base. Is that correct? So you should note this point, okay, that electron deficient hydrides will act as Lewis acids, whereas electron rich hydrides will act as Lewis base. Okay, 13th group, electron deficient. 14th group, electron precise. 15th, 16th and 17th group, okay, what? Electron rich or Lewis base hydrides. Understood? So that's about covalent hydrides. Okay, now we shall talk about the next type of hydrides. What is that next type of hydride? Yeah, okay, we will be talking about the next type of hydrides known as metallic hydrides or non-stoichiometric hydrides. Okay, metallic hydrides, okay, yes, hydrides, okay, or they are also called as non-stoichiometric hydrides. They are also called as non-stoichiometric hydrides. Understood? Okay, so when you get metallic hydrides, okay, look here, if hydrogen combines with D block elements, and okay, when hydrogen combines with D block elements from, okay, group 3 to group 5, okay, from group 3 to group 5, okay, I have told you, hydrogen does not react with the elements of group 6, 7, 8, 9 except chromium. Okay, that is why I am telling you, if hydrogen reacts with D block elements from group 3 to group 5, okay, it will form what type of hydrides? It will form metallic hydrides. I'll give you some examples. For example, lanthanum hydride with the formula La. Observe the formula here, very important. The formula is very important. Lanthanum hydride, it is LaH, okay, 2.76. Look here, Yes, hydrogen 2.76, vanadium hydride VH 0.5, nickel hydride 0.7. Okay, yes, what is the ratio here? The ratio is 1 is to 2.76. Here the ratio is 1 is to 0.5, and here the ratio is 1 is to 0.7. Okay, 1 is to 0.5, 1 is to 0.7, and 1 is to 2.76. That means here the ratio is not a simple whole number ratio. It is not a fixed whole number ratio. It is it is not a fixed whole number. 1 is to 2.76, it's a fraction. 1 is to 0.5, 0.5 is a fraction. Okay, 0.7 is a fraction. So here the ratio is not a simple whole number ratio, it's a fraction. That is why they are called as what? Non-stoichiometric hydrides. Okay, that is why they are called as non-stoichiometric hydride, because the ratio is not a simple whole number ratio. Okay, it has become a fraction, therefore they are called as non-stoichiometric hydrides. Okay, understand this point, guys. In the 12th standard we have a chapter called as solid state. See, there we come across lattice points and voids. Lattice points and voids. Observe here, if I take lanthanum hydride, okay, lanthanum hydride will occupy the lattice points. Lanthanum will occupy the lattice points. Lanthanum will occupy the lattice points, whereas hydrogen will occupy the voids. Hydrogen will occupy what? Voids. Are you getting my point? Okay, lanthanum is occupying what? Lattice points, whereas hydrogen is occupying what? Voids. That is why, okay, yeah, the ratio is not a simple whole number ratio, it has become a fraction. Okay, I hope it is clear. So such type of hydrides are called as metallic hydrides. Do remember one more property of these metallic hydrides. These metallic hydrides are good conductors of electricity. They are good conductors of electricity, good conductors of electricity even in solid state. Even in solid state. Are you getting my point? Even in solid state. Okay, so they are, all these metallic hydrides are good conductors of electricity even in solid state. Okay, hope you have understood. Now guys, we have to understand something called as adsorbed hydrogen. Adsorbed hydrogen. Okay, look here, hydrogen, okay, will get adsorbed on these metal surfaces like lanthanum, as I said, like nickel, as I said. Okay, if I take up nickel, hydrogen will get adsorbed on the surface of nickel. Hydrogen gas will get adsorbed on the surface of nickel. What do you mean by hydrogen? What do you mean by adsorption? I'm not talking about absorption. I'm talking about what? Adsorption. Okay, what do you mean by adsorption? Yeah, so what is adsorption? See, if the particles of one substance, if particles of one substance get accumulated on the surface of another substance, if particles of one substance gets accumulated on the surface of another substance, that is called as adsorption. Look here, I am writing with a piece of chalk on the surface of the board, isn't it? I am writing with a piece of chalk on the surface of the board. What is happening? The chalk particles are getting accumulated on the surface of the board, isn't it? That is called as adsorption. Here also, hydrogen gas, the atoms of hydrogen gas gets accumulated on the surface of nickel. Okay, this acts as an excellent catalyst. It acts as an excellent catalyst, and that type of catalysis is called as catalytic hydrogenation. It is called as what? Catalytic hydrogenation. Catalytic hydrogenation. For example, look here. If I take ethene and treat it with hydrogen in the presence of nickel as catalyst. Okay, if I take ethene and treat it with hydrogen in the presence of nickel as catalyst, what is going to happen here? Hydrogen gas gets adsorbed on the surface of nickel, and this will become an excellent catalyst, wherein now ethene will be reduced to ethane. Okay, ethene will be reduced to ethane. Such type of reduction or such type of what? catalysis, where catalyst, what is this catalysis here? We are adding hydrogen in the presence of nickel as catalyst. Addition of hydrogen in the presence of nickel as catalyst is called as catalytic hydrogenation. So guys, so this is all about, okay, hydrides. So far we understood what are ionic hydrides, covalent hydrides, different types of covalent hydrides like electron rich, okay, electron precise, electron deficient, and then we understood what are metallic hydrides. Is that correct? So based on all this concept, now we will solve some MCQs of MTG fingertips. Okay, yes students, I have this question. On moving from left to right in a period, what is the order of acidic character of hydrides? Okay, what is the order of acidic character of hydrides? Guys, I have ammonia, I have water, okay, and I have hydrogen fluoride. Okay, yes. What do you mean by an acid? Acid is any substance, okay, acid is any substance which donates what? Yes, H plus ion when dissolved in an aqueous solution according to Arrhenius theory, correct? Acid is any substance which donates H plus ion when dissolved in an, okay, aqueous solution. So I have ammonia, I have water, and I have fluorine, hydrogen fluoride. Okay, and what is the order of electronegativity here? Okay, fluorine is more electronegative than oxygen, oxygen is more electronegative than nitrogen, isn't it? Fluorine is more electronegative than oxygen, oxygen is more electronegative than nitrogen. Is that correct? See, now, okay, if I have to call this ammonia as an acid, ammonia should donate H plus ion. If I have to call water as an acid, water should donate H plus ion. Okay, if I have to call hydrogen fluoride as an acid, it should donate H plus ion. Look here, if I take ammonia, NH3, it should donate H plus ion and it forms what? NH minus. Water, H2O, okay, yes, it should donate H plus ion and it forms what? OH minus ion. Hydrogen fluoride, okay, it should donate what? H plus ion and it forms what? Fluoride. Observe here, fluorine is more electronegative than oxygen, than nitrogen, isn't it? Since fluorine is more electronegative, it will quickly, okay, yes, withdraw the shared pair of electrons from hydrogen. It will withdraw the shared pair of electrons quickly. As a result, hydrogen will be eliminated as H plus ion. Okay, now if a substance donates H plus ion easily, it's going to be a strong acid. If the substance cannot donate H plus ion easily, it's going to be a weak acid. Here fluorine is more electronegative, therefore it will withdraw the shared pair of electrons. As a result, hydrogen will be eliminated as H plus. Here also oxygen is electronegative. Okay, oxygen withdraws the shared pair of electrons from hydrogen. If I take water, look here, HOH. So oxygen will withdraw the shared pair of electrons from hydrogen. So hydrogen will be eliminated as H plus ion, no doubt. But when compared to fluorine, oxygen is less electronegative. Fluorine is more electronegative. Okay, so what is the order of acidic nature here? Hydrogen fluoride is a strong acid than water. Water is a strong acid than ammonia. So therefore the correct option is option A. Understood? Yes. Next question. We'll go with the next question. Which of the following hydride is electron deficient? Okay, if he is talking about electron deficient, that means he is talking about covalent hydrides. For covalent hydrides, hydrogen should combine with, for covalent hydrides, hydrogen should combine with what? Come on. Okay, 13th group should combine with P block element. P block element, isn't it? Hydrogen should combine with P block element. If hydrogen combines with 13th group element, it is electron deficient. Is that correct? Yes. If hydrogen combines with 14th group element, electron precise, isn't it? Okay. Yes. If hydrogen combines with 15th group elements, 16th group and 17th group, then we'll have electron rich. So 13th group elements means boron, aluminium. Okay, come on. Boron, aluminium. Okay. Yes. Gallium, indium and thallium. Okay, these are 13th group elements. 14th group elements, carbon, silicon, germanium, okay, arsenic, okay, tin and lead. tin and lead. Okay, so you just remember these examples at least: boron, aluminium, carbon, silicon. In 15th group, nitrogen, phosphorus. In 16th group, oxygen, sulfur. In 17th group, halogens: fluorine, chlorine, bromine, iodine. That's it. At least remember all this. Now he's talking about electron deficient. Electron deficient means 13th group. 13th group means either boron or aluminium. Now, where is the answer? Yeah, we have this answer. What is it? Okay, B2H6, isn't it? So with carbon, that is 14th group, we will get electron precise, isn't it? With calcium, that is S block. With sodium, S block. What type of hydrides are formed? Ionic hydrides are formed. He is talking about electron deficient, so that means that is nothing but B2H6. That's the correct answer. Yes, we'll go with the next question. Okay, what is it? Which of the following hydrides is not, okay, which of the following statements regarding hydrides is not correct? Yeah, it is not correct. Which of the following statements regarding hydrides is not correct? Okay, the first option says ionic hydrides. Yeah, I have discussed all this. Okay, ionic hydrides are crystalline. Correct. Ionic hydrides are non-volatile. Correct. Okay, ionic hydrides are non-conducting in solid state. This is also correct. Yes, all of them are correct. Ionic hydrides are crystalline. Correct. Ionic hydrides are non-volatile. Correct. Okay, they are also non-conducting in solid state. Okay, electron deficient hydrides are Lewis acids. Yes, that is true. We have discussed this. Okay, elements of group 13. Elements of group 13 will act as electron deficient, okay, hydrides. Yeah, that's correct. Elements of group 15 to 17 are electron precise hydrides. No. Okay, elements from group 15 to 7 will form what type of hydrides? Electron rich hydrides. Electron precise hydrides are formed from, okay, which group? 14th group. Therefore the incorrect statement is option D. Elements of 15th to 17th group, they form electron rich hydrides, not electron precise hydrides. Understood? Yes, that's correct. Okay, next question. Okay, in group 6, the only metal which forms hydride, okay, this metal is, I told you, hydrogen. Okay, hydrogen will not combine with the elements of group 6, 7, 8, 9 except chromium. Okay, it will form chromium hydride with chromium. It will form an hydride with chromium. So what is the correct answer? It is chromium, isn't it? Okay, well students, so that's all about the MCQs regarding hydrides. In the next video, we will talk about one more compound of hydrogen. What is it? Water. Okay, thank you so much.